So yeah, I repeat, the setting that we're working in is with a lot of clients who have contributions in a very sparse domain. So this domain could be something like URLs or strings. And that means if we want to aggregate a histogram over those, so we want to count how many times a certain string appeared, we will have in this histogram lots and lots of zeros, right? So lots of strings will never appear. And that poses a challenge for implementing this protocol. The statistic itself is something very interesting. So we will find histograms all over the place in many analytics computations. But at the same time, it can be very sensitive, right? So if these are strings and, for example, URLs that have a security token embedded, then you don't want your unique security token to appear in the final output because that will be sensitive information about you or for you. So how can we compute this histogram while still respecting privacy, right? Also the individual inputs we don't want to reveal. So this is TPMPC. So naturally, we're going to consider multi-party computation as a solution here. And as you all know, TPMPC tries to approximate this real world where we have this black box functionality F. We just give all our inputs, so all the clients turn in their inputs into this functionality, and we get out the result that we want. For example, a private histogram. In the real world, we don't have this functionality, so what we do instead, we have this protocol Pi that tries to emulate this functionality. And so we get an output, and we want to ensure that this output is computationally indistinguishable from the ideal world. In particular, even if some of the clients or servers are malicious. So these red horns here indicate that a party is malicious. So in the setting we're considering here, we want to distribute the trust. And we're working in a particular setting of MPC, which is the two-server setting. That means we don't distribute the trust across the clients. So for the clients, we can assume any arbitrary number of malicious clients. But we want to have two computation parties of which we assume one of them is not malicious, so it's honest. Yeah, the way we can then conceive a protocol is to say the clients encrypt their inputs to the two servers. The servers run a 2PC on the encrypted inputs that they got, and then finally the servers receive the result. Right, so that's a very high-level view of what you can do. Here's again a schematic of that. So distribute to two servers, run a 2PC, retrieve the output. Now, are we done here? So can we just implement this in some NP speeds or whatever? And does this give us a protocol? Well, one challenge is that the output itself is not private. So if you think of this histogram and we would just give it to someone in the clear, again, you could see very unique strings in this histogram. Like every string that appears only a single time will appear in this histogram. And if the string itself is sensitive, then that means the histogram itself is not private, right? Even if we don't know which client contributed to which string. So we need to do something better for the output. And the approach I'm going to take here in this presentation is differential privacy, but in the talk before, we just heard that for some functionalities, maybe that's not needed. So the goal in differential privacy is to make the output similar or the same, independent of one particular user's input. So that means for every user, we have the guarantee that the output will not change by a lot, whether that user is included or not. And the way to do that in a central model, so if we have a central server that computes the histogram, there are actually lower bounds and matching upper bounds for exactly that functionality. And the protocols, they all work like this. So we compute the histogram in the clear without privacy. Then we add some noise, which can be Gaussian or pass noise, to each of the non-zero entries. And then we threshold, meaning everything that doesn't pass a certain threshold, we just set to 0. And afterwards, we reveal the resulting histogram. So our goal now is to implement exactly this algorithm in the 2PC setting with malicious security. And of course, the assumption here is that the resulting histogram is still useful, so that we actually, for our application, we don't care about the rare inputs. But again, if that's your goal, then maybe you can't have privacy. So now the question is, who implements this trusted server, right? So how can we implement this? And we don't want the central setting, right? The central party that implements it. So again, we're going to go to MPC and try to emulate it with that. Or at least with something resembling MPC. And I'll get to what exactly that means in a second. Yeah, now the big goal here is to make this efficient. And some of you who have been at TPMPC last year in Aarhus might remember my talk there, where I talked about how to do this in a semi-honest security setting. So there we have a pretty efficient protocol that was presented at CCS 22. So the focus of this talk is to get malicious security for exactly that setting. But I'm going to repeat a little bit of the threat model and the details of that. So again, we have these two servers and the adversary can control one of the servers, but not both, and any number of clients. And what we want to guarantee is that, yeah, even with malicious security, so even if the servers and the malicious clients arbitrarily deviate from the protocol, we still have security against the honest clients, for the honest clients, privacy for the honest clients. And in particular here, we are working in the universal composability framework, so like this very strong notion of malicious security. And then for the output privacy, we have different privacy that then protects the privacy of individual clients. We are not achieving the ideal of MPC, so this ideal functionality that does not leak anything, but in fact our functionality will be leaky and it will reveal something more than the actual output that we want. But what we guarantee for this output is, again, that it's differentially private. So our output is differentially private and the leakage of functionality has is differentially private, which means overall the protocol reveals only differentially private information about clients. And differential privacy also implies some weaker guarantees about groups of clients, which this slide is here. Okay, so we don't want to do work in order of the domain size, because as I said, this can be huge, this can be strings, exponentially large. We want very lightweight clients, so think phones. We want clients to be able to send a single message and then disappear, so they don't have to stick around for the entire computation. So the bulk of the computation must be on the servers, and we want to avoid generic MPC just because it's very expensive. The tools we're going to use is, for once, linearly homomorphic encryption. So for those who don't know, we have encrypted values that we can then perform linear operations over, which means adding to encrypted values or multiplying by a constant or adding a constant. And then another tool that we're going to use that is very important for the malicious setting is zero-knowledge proofs of knowledge. And with that, basically the prover can convince the verifier that they know a secret without actually revealing that secret. But then they can also prove some constraints about that secret. For example, that it is less than a certain number or something like that. Okay, the high-level idea, and now this is a repetition of last year's talk, is as follows. The client starts with an index value pair and basically encrypts the index, the hash of the index as well as the index itself and the value, and sends all of these encryptions to the first server. Now, the first server shuffles everything just to make sure that the order doesn't reveal anything to the second server, and then homomorphically computes the OPRF of the index, so a pseudo-random function of the index, under the encryption. And that is being sent to the second server. So here the PRF is this well-known construction, hash of x to the key of the first server, which can be done homomorphically under this encryption scheme. The second server now can decrypt the OPRF values, and it doesn't know the actual indexes, it just knows pseudo-random indexes. And then it can group by them, it can aggregate by all the ones that have the same pseudo-index, and sum up the values homomorphically. We can then send these encrypted buckets now, so these only consist of the encryptions of the index and encryptions of the sums of the values for each index, so that's already the histogram. Send that back to the first server under encryption. Both parties add noise, so this is the noise adding step of the private histogram algorithm. And then only if a value passes a certain threshold, we decrypt. And those two steps here, they're modeled as arbitrary MPC. In practice, of course, we will have a particular protocol implementing those. And then the histogram, the output is this malicious histogram. So that's already a pretty complicated protocol, right? So it's just in the semi-honest setting, we already have a lot of steps, messages flying left and right. But what can go wrong here, right? What can go wrong in this protocol if we have malicious parties? So one thing is that this encrypted histogram that we have, so even the one where we don't know which index which pseudorandom index corresponds to which real index, already leaks something about individual clients. And the reason is here that we haven't added any noise, right? So this will change whether a certain client is in there or not with constant probability. So there's no randomness in there. So we have to introduce randomness already before aggregating, which means that the first server has to insert some dummy records that basically try to hide whether a particular client is in there or not. Okay, so in the malicious setting, things become even worse. Because remember, like in the first message, we send the hash of the index and the index itself encrypted. Now a malicious client could just say, well, maybe I'm going to send the hash of something else and my index, and there's no way to tell, right? So we need to make sure that inputs are consistent here from clients. A second thing that can go wrong is when shuffling here and inserting dummies, maybe we don't shuffle, right? Maybe we do something else instead of shuffling, like dropping clients, multiplying clients, homomorphic computing on clients' inputs, anything like that, right? So the first server also has a lot of ways to screw up the computation. And now, finally, when we do this aggregation, right, the second server doesn't need to aggregate, actually, right? It could do anything else but aggregate. It could like aggregate things that don't belong together or arbitrarily add numbers to the results and so on. So again, we have a lot of ways of screwing up the computation here. So this protocol has not a big chance of taking it as it is and making it maliciously secure without just proving every single step of the computation, right? You're doing very variable computation for every single step, which again is very expensive. Okay, so yeah, and again, all the subprotocols also have to be maliciously secure. So these, again, introduce new points of failure. As you can see, things become very expensive and complicated here. Yeah, so again, this is a more detailed overview of the attacks that can be run. So malicious clients can make the protocol abort by being inconsistent. And one way we can solve that is just making sure that we prove the client's input is in a certain range and is consistent, that they actually encrypt the same thing, and the value is not some arbitrary value that screws up the computation. So use a range proof here. The second one is the OPRF we use is actually really hard to make maliciously secure because it involves a hash, right? And we cannot reasonably prove that we evaluated the hash function correctly in zero knowledge. So the way we solve this is to switch to a different pseudo-random function, which in our case is this d2s1-2 PRF. And that one lends itself much more to compute zero knowledge proofs over. So we can just use a simple signal protocol to prove consistency of the OPRF values. So yeah, since we're not relying on this random oracle or something. Now for the servers, there are 4 possible attacks. So some I mentioned, right? We can drop clients' contributions, and actually there's nothing we can do because we are aiming for these one-shot clients. So we want the clients to be able to send a message and disappear. And there's no way you can distinguish that from the client, like the server dropping the message from the client not sending the message. You cannot distinguish that. So the client cannot send in a way that is ensured it delivers. So that would imply some broadcast protocol. Also, the server can change the noise distribution. So when inserting dummies into the protocol, it can change the distribution arbitrarily. In particular, it can choose to not add noise, right? So it can say, well, I don't want DP. I'm going to let the second server learn anything. But also we cannot fix that because in particular, like the first server revealing its input to the second server, you cannot avoid that, right? So you have to assume that if the first server is malicious, then whatever the second server learns, we don't care. But then there's still other things that we have to protect against. So one is duplicate or honest client's input. So for example, instead of aggregating the result of 1 million clients, we just take the first client, we duplicate its input 1 million times, and then we aggregate that, and then add some noise to that. But of course, it's clear that this breaks privacy, because now we see exactly what this client has as input. And then also a second thing is that aggregation can be messed up by both of the servers or the servers who do the aggregation. So the first thing we're going to solve by using proofs of plaintext knowledge. Basically, in order to accept a client's contribution as valid, we have to also accept a proof that you know the input to that. So you know the value that was encrypted. And now the second server either can duplicate the proof and the input, but then that's clearly visible, or it cannot produce a proof for whatever duplicated input it got. And then the second thing, so messing up the aggregation, we solve that by doing the aggregation in the clear. So since it is done under homomorphic encryption, right, the aggregation or the pre-aggregation ciphertext can be revealed to both servers. They don't reveal anything if the key is secret shared. So now, instead of having one server aggregate, as in the semi-honest model, in the semi-honest protocol, we just have both servers aggregate in the clear and then jointly perform the decryption. So that now the servers can check each other's work. If like one of them deviates, we know, okay, something went wrong. We don't know who did something wrong, right? We cannot blame the other server, but at least we can abort the protocol and know, okay, somebody cheated, somebody cheated. Okay, now one issue that seems like we've solved everything, but the differential privacy story now also becomes even more complicated. So remember before we had the client who just sends its inputs to the first server. First server adds some noise, sends it to the second server, whose view is no DP, so the second server doesn't learn anything. And then the second server gets this anonymous DP histogram and can perform the aggregation locally. Now, in the new protocol, what we will have is first server adds noise, so the second server's view is DP. Then the second server has to add noise, so the first server's view is DP, so we have twice the dummies, twice the shuffling, and so on. And now both of them get this anonymous histogram as part of the decryption. And the noise here is not independent of client inputs. So this is, again, the noise itself can reveal something about client inputs, so we have to make sure that this doesn't leak. And malicious noise here could result in some leakage, right? So we have to ensure that a server adding noise and then later seeing the result of the noise aggregate doesn't learn anything by maliciously perturbing its noise. So in a classic DP setup, to maybe elaborate a bit more on this, is we have data, we generate noise, we get noisy output, give that to the adversary, we then prove that the output didn't change a lot for the single client. What we have here is we have client data, we generate noise, we get noisy leakage. We then have some influence on the functionality because we're choosing inputs, right? We're choosing noise values, which then, again, we can generate noise, we get some leakage, and then this entire thing is modeled as a big MPC functionality, which has DP leakage, and for that we have to prove that it's equivalent to the classic set. So for theory enthusiasts, the way we did it in the protocol, for which I don't have slides, but basically what we did is we showed that this interactive algorithm leaks the same as the central mechanism from a DP perspective, so that you can directly reduce it, but that's not a generic solution. So it's not clear how the write setup, like the interactive mechanism, how that can always be reduced to a clear central DP setting. So this is an open theory question that we have in our paper. Okay, but I think with that I have enough for showing the full protocol. And again, I'm not going to go a lot into the details. In the end, I'm going to show you how the full protocol looks actually in detail, but there's no way we can fit that into a talk. So now what we have, we encrypt the index, we encrypt the values. We don't have this encrypted hash of the index anymore because we're using a different OPRF. And so we don't have to prove consistency between those. But we have to attach this proof here from the client that, in fact, the encrypted index is an encrypted index and that the value is under certain ranges, not a random value. We send this to both servers, who now both locally perform shuffling and add dummies. And again, they have to, for the dummies, they have to insert the proof of plaintext knowledge for the index, as well as proof that the value in fact is 0. So the dummies, they don't contribute to the final histogram. We shuffle those dummies with the original plaintext together using a shuffle proof. Again, that's a step that might be expensive, but actually it's reasonable in practice. And then perform the OPRF under encryption. And the nice thing here is, again, as I said, this d2s1-2 OPRF was chosen because it is nice to prove over. So it's possible to prove correct evaluation of it using a simple Sigma protocol. So just a couple elliptic curve operations, but nothing too hard. So in particular, no snarks or anything like that. Yeah, then both parties get this encrypted output. So the encrypted pseudo-random histogram, if you want, with dummies, and can locally perform the aggregation. So they can locally reveal the OPRF values, group by OPRF values, homomorphically sum up the group values, and then get the result and actually check that each other that they get the same result. Finally, we can homomorphically add noise. So everything is homomorphically encrypted here, so we can add the noise like that. And then run a protocol, which I'm not going to go into, that just implements this threshold functionality. So that checks whether a value is over a certain threshold, and if it is, reveals the index that was encrypted. Now both parties get the output histogram, and we have the desired target functionality. So the way to implement the Slowly and Polsky OPRF under encryption requires a particular homomorphic encryption scheme. So there are multiple ways to do it. One in prior work was using this Khamenei-Shoup encryption scheme, but the issue here is that it makes the Sigma protocol a little bit more complicated, because now the group order that we have for the OPRF and the plaintext space of the encryption scheme, they don't match up. And you can't really make the match up, so what you have to do is perform some more complicated masking under the encryption, and again provides the notables for those. So what we did instead, with Leonard's help, because Leonard is good at these things, is using a CL-based, class group-based encryption scheme, where you can make the cipher, the plaintext space, and the OPRF domain the same. And that again makes your proof much simpler, at the cost of introducing some maybe non-standard assumptions. Okay, now another thing that is Leonard's big contribution to this work is to model it as a UC ideal functionality and then prove the entire protocol secure under UC. But this is also like one of the things that is hard to put in a talk, and you will see why. So this is the functionality, and the protocol is not any shorter either. So if you want the details of that, I encourage you to look into the paper. Okay, to summarize, so we have a new protocol for sparse histograms with malicious security, as opposed to previous semi-honest work. We have differential privacy of the outputs, as well as any additional leakage during the protocol for the clients. And the challenges that we had while developing this was combining malicious security with differential privacy. And as I said, there's an open theory question there of like how to nicely model secure computation with DP leakage in a malicious security setting. So there's this non-standard interactive DP process that happens to work for our protocol, but maybe doesn't for every other one. Yeah, with that, I'd like to thank for your attention and open to questions.